Hi everyone, welcome to our discussion of categorical data, our topic for week 2 of STAT E100. In our discussion of categorical data, this is part of our broader discussion of descriptive statistics. So we've already covered data, really what a data set consists of, the different kinds of variables you encounter, and the different types of studies that you will see when you conduct research or interpret research. So you might find observational studies or you might find experimental studies. For this week, we're going to talk about categorical data, how to analyze it, how to visualize it, and so on and so forth. So in particular, we're going to focus in part 1 on frequency tables, or tables of counts, and we're going to examine how you can graph or visualize one categorical variable. For part 2, we will talk about contingency tables for two categorical variables. So this is the case in which you have two variables and you want to examine the counts or the percentages or proportions for two categorical variables. For part 3, we will look at graphs for two categorical variables, various ways of visualizing two categorical variables. So with that in mind, let's start our discussion today on categorical data. All right, for part 1, we're going to talk about frequency tables and graphs for one categorical variable. Let's think about John Jacob Astor IV. He was a prominent, wealthy Harvard man, so he graduated from Harvard University. He was born in the 1860s. He was also a science fiction novelist. He was an inventor and he was a lieutenant colonel. And he made a fortune in real estate. In fact, he built the Waldorf Astoria Hotel, and we have a picture of him right here. At one point in his life, he was worth around $1.7 billion. Now, the thing is that in 1912, he and his wife boarded the Titanic. And he was an incredibly wealthy, white, able-bodied adult male, so he was fairly fit. The question I want to pose, suppose you're a historian, and ask yourself, did this man survive the Titanic? And so let's collect the following data. This is real data on the Titanic. And so you can see we have these cases, and the cases are passengers of the Titanic. These are the first several rows. And then we have several variables. These are the characteristics of the passengers. Each column, as we talked about, is a different variable. And you can see that we have this variable for whether or not the person survived, so it's yes or no. We have a variable for whether the respondent is male or female. These are both categorical variables. And then we have this variable for passenger class, whether you were in the lower, middle, or upper class. When you purchased a ticket on the Titanic, you were put into different classes based on your fare and the accommodations that you received. And then we also have this variable for the passenger's full name. So we can actually identify in our data set where John Jacob Astor IV is located, and we can actually see, did he survive the Titanic? Before we do that, I want to keep in mind what categorical variables really are. They are variables that have values with different categories or qualities. Sometimes they're called factors, and the different categories are called levels. So we've went through some of these examples before, but it's like gender of respondent, approval or disapproval of a social policy, whether or not you're a regular smoker. So in our data set, all the variables are categorical. Now I've highlighted here John Jacob Astor IV. And if you look through that row identifies the data, the observations on him. And you can see that he in fact did not survive the Titanic. Now this raises some questions. You might ask, he was an upper class man, but he didn't survive the Titanic. What percentage of passengers overall didn't survive? And what proportion of passengers were in the upper class, you might ask. And you might also ask how many women were on the Titanic as well. It's these kinds of questions where when you look at particular rows of a data set that can really prompt investigation of various ideas. So to answer these kinds of questions, we will want to create tables and graphs for a single categorical variable. One way to really create a table of counts is through frequency tables. A frequency table is just that. You take a categorical variable and you just calculate the counts of observations for each category. Frequency is just a fancy word for counts. So if you ever hear the word frequency, think counts. You're just counting up how many in each category in terms of observations. So right now I want us to focus on how many people survived the Titanic and how many did not. Meaning, if you put John Jacob Astor in the context of the data, was he unusual or was this typical of him surviving? Well, the easiest way to do this is just to create a table of counts. This is a table of counts right here. So we have these two categories of this variable survived. Survived is the name of the variable. And you can see we have no and yes. So we have 618 people who did not survive and 427 people who did survive. And then we have that total. So we have these counts, and then we have these counts of observations for all categories. So you can see that the total size of the data set, the number of observations is 1,045. Besides a table of counts, you can also create what's called a relative frequency table. Sometimes a relative frequency is more useful. So a relative frequency is simply a proportion or percentage of each category. So to calculate the proportion, you just divide the counts by the total number of cases. And then that will give you the proportion, but usually we want to multiply by 100 because often people like to express proportions as percentages. So we call this a relative frequency table, and it's simply a table that gives the categories of a categorical variable, and it gives the proportions or percentages of observations for each category. So here we have our Titanic data on who survived, and on one table we have just the counts. So we have 618 people did not survive, 427 people did survive. And then we have a table of proportions, and we simply calculated that by taking the counts and dividing by the total size of the data set. And then, so you can see for the no category, we have 618 observations within that category, and the total number of observations is 1,045. You divide 618 by 1,045, and you get 0.59. That is the proportion of observations, the proportion of passengers who did not survive the Titanic in our data set. And we could also count this proportion for, calculate this proportion for those in the yes category. So we can see that 427 people survived the Titanic out of a sample size of 1,045. And when you just calculate that fraction, you get 0.41. So we find that about 0.41, that's the proportion of people on the Titanic who did survive. So you can see that John Jacob Astor, he was actually in the majority category. Most people on the Titanic did not survive. And then I'll briefly mention that the total should equal 1. If you're calculating the proportions correctly in a relative frequency table, the total proportion should be 1. So 0.59 and 0.41, they add up to 1. Often, though, we want to express proportions as percentages. So the way you do that is you simply multiply the proportions by 100. So when you multiply 0.59 times 100, you get 59%. Similarly, when you multiply 0.41 times 100, you get 41%. And when you multiply 1 times 100, because the total proportion is just 1, you get 100%. So when you display your data to an audience, they usually like percentages. And so we can conclude that 59% of passengers did not survive the Titanic, and 41% of passengers did survive the Titanic, and the total is 100%. So we have 100% of the passengers. Now, when we look at this relative frequency table for surviving the Titanic, it looks the same. So we have categories, we have the percentage of observations, and we just have the total number of observations. Now, one thing to keep in terms of percentage, the one thing you should keep in mind, however, is that sometimes there'll be a slight rounding error. So if you don't quite get to 100%, it should be pretty close, because sometimes you might round a percentage up or down, so it might be a little bit off. So let's examine our research questions in the context of creating these relative frequency tables. You might say, what percentage of passengers didn't survive? So you could just create a relative frequency table of percentages. In terms of the question, what proportion of passengers were in the upper class? You could, for example, create a relative frequency table of proportions, or maybe you want percentages if you want to display that to an audience who might understand percentages more than proportions. In terms of the other research question, how many women were on the Titanic, you might create a frequency table of counts. So you can see that these research questions are quite easily answered through a collection of data and then this kind of basic analysis where you create a table of counts, proportions, or percentages. Now, besides tables, it's often useful to visualize a categorical variable. So to to really visualize a single categorical variable, it's very common to either use a bar graph or a pie chart. Bar graph is usually preferred by statisticians. A pie chart is thought to be somewhat misleading. A bar graph, which we'll talk about in just a second, a bar graph shows the bars whose areas are representing the count of observations for each category of a categorical variable. A pie chart, it basically shows how a whole is divided into categories, and it shows wedges of a circle, and each wedge has an area corresponding to the proportions for each category. So let's look at a bar graph of surviving Titanic. This is a bar graph of counts, so it's a frequency bar graph. And I've presented the frequency table for comparison, and you can see that the bar graph just duplicates the findings from the frequency table. But sometimes it's useful just to visualize the difference, especially to really understand the differences between the number of observations in each category. So the bar graph clearly shows that we have more people who did not survive the Titanic than those who did survive the Titanic. Here's a pie chart for surviving the Titanic. It's similar, so it shows that it's based on a frequency table of counts, but the wedges give you an idea of the relative proportion or percentage. And so you can see that replicating the bar graph of frequency counts, you do see that more people did not survive the Titanic than did survive the Titanic. Now, if you talk to statisticians, they typically don't like pie charts. Now you might ask why that is, because you see pie charts everywhere. The reason pie charts are somewhat frowned upon among statisticians, especially those who are experts in visualizing data, is that with a pie chart, it can be very difficult to compare group sizes. And the idea is that you don't really have a common benchmark. So in a bar graph, you can really easily compare the heights of the bars. With the pie chart, it can be pretty difficult to really compare the relative sizes, especially when the categories are pretty similar, the number of counts or the relative size of the counts, meaning the proportions or percentages. So I just want to emphasize that if you're showing a table of counts or frequencies to a statistician or an expert in data visualization, you should probably present a bar graph. So let's just examine this. So this is a bar graph of the counts for the different passenger classes on the Titanic. So on the Titanic, you had people in the lower, middle, and upper class. This is just based on how much you paid to be on the Titanic. And you can see that in the bar graph, it's quite clear that most people on the Titanic were in the lower class. And then the next highest category was really the upper class. You had more people in the upper class, and the middle class actually had the fewest number of passengers. On the pie chart, the difference between the middle and upper class, it's almost impossible to distinguish. Yet on the bar graph, even though the middle and upper class number of counts is very similar, you can still distinguish between the two categories, meaning you can still tell that there are more people in the upper class than the middle class. The pie chart, it really kind of washes that over. This is why bar graphs are typically favored by statisticians and experts in data visualization. Creating good graphics is a very important part of data visualization. So I think it's important to talk about some of the ways in which you can really create good graphics, some of the principles that really lend itself towards data visualization in an effective way. And the other part about this is that a lot of applied statistics entails graphic design, entails creativity. And especially in recent years, the whole topic of data visualization has really had a renaissance within statistics, because people are finally understanding how important it is and actually how difficult it can be to present a set of data effectively. So let's go over some of these principles for creating good graphics. So here are some things to avoid: biased labels, misleading scales, having no scalar labels on any of the axes, excessive visualization, so this is sometimes called a low data to ink ratio, which we'll cover in just a moment, and then unequal areas. In other words, a really violation of what's called the area principle. So let's go over these. Biased labeling is one of the things you should really avoid when creating a graph for statistical purposes. you really should just avoid loaded words or phrases that might prime the reader in a way that really biases the reader. So in this case, we have a bar graph, and we really have this biased label for the lowest category. It's really pejorative, and you should really avoid that. Try to be as neutral as possible in the labels for your categories, for your titles, for really as all the labels and information that you put in text on a bar graph. Try to make it neutral and just really try to convey what's going on. The data should speak for itself. Another thing you should avoid is misleading scales. In other words, avoid truncated scales, so really shortening the scales to artificially inflate the effect size, or you should avoid irregular scales. So here's an example in which we've truncated the scale for frequency, the number of counts, and you can see the scale jumps from 0 to 300, but it's not quite apparent. And this sort of truncation of the scale really makes it look like the lower class number of counts is vastly more than the middle and upper class. And it makes it appear that the upper class and middle class are extremely small. It's really artificially inflating the number of counts visually in the lower class. So try to avoid a distorted or truncated scale for your axes. Another problem that can go on is having no scale or labels. So you should make sure to include all appropriate scales or labels with the point to convey your findings effectively. So in this case, we have this bar graph. It's the same bar graph of passengers on the Titanic by class. And you can see that there's no scale. So it's unclear whether this is a bar graph of proportions, percentages, counts, or something else entirely. So always make sure to include a scale or labels. Another problem could go awry if there's no sort of labeling of the different categories. So if we avoided lower, middle, and upper class labels, and there were no labels, that would also be misleading. So always make sure that you're putting in the appropriate labels so that your reader can interpret your findings. Something else that is quite common in data visualization that should be avoided is excessive visualizations. In general, you should avoid excessive decoration or visual clutter. This has been called a low data to ink ratio. Okay. What you want is you want a high data to ink ratio. The general idea is that any graph you create for statistical purposes, it should convey as much information about the data, so it should have a high data to ink ratio. So what really constitutes a low data to ink ratio? Meaning what constitutes a graph that doesn't say much about the data yet spills a lot of ink? Well, redundant information, if you have colorings that it's just really not informative, that's unrelated to the data, if you have overly fine-grained axes, tick marks, any of this sort of excessive visualization, that can really lead to this low data to ink ratio that can really overwhelm the reader and really add this sort of clutter that makes your statistical graph misleading. Now this is not a science, this is an art. This is where statistics is about graphic design. But I think if we go through a few examples, you'll see sort of what should be avoided. So here is a statistical graph of passenger class on the Titanic. So you can see we have lower, middle, and upper classes. And then the axis is labeled. But we have this legend, also called a key, and it shows the different colorings and what the labels are. The problem is that this is totally redundant. It's excessive decoration. You don't need it. And it can actually just be misleading because the reader might think that it's something else different. And it's also just pretty ugly if you have all this redundant information. So we want to remove that. But once we've removed it, you can see the colors of the different bars. They're also not needed because they already have different labels. The reader already knows that these different categories are part of the same categorical variable. So we should also avoid the color. So when we remove the color, we have this kind of bar graph. And this is really better. This is really a bar graph with a higher data to ink ratio, meaning you're saying more about the data with less ink on the paper. So it's useful to compare these two graphs. The one graph has a low, relatively, data to ink ratio. The other one is a high data to ink ratio. You want to say as much about the data with as little ink or visualization as possible. Another problem that can occur in creating a statistical graph is unequal areas. The basic idea of this is called the area principle. The sort of snapshot idea of it is that the area occupied by any part of a graph, it should correspond to the magnitude of the value it represents. And so one thing you should really avoid is 3D visualizations, because this can really violate this idea of the area principle. It can imply that certain wedges or certain bars are much larger than the other just by virtue of the way they're presented in a 3D context. So here's another example in a 2D context of violating the area principle. This is just the same bar graph of counts for the different categories of the passenger class variables. So you can see we have lower, middle, and upper classes, and then we have a number of counts. However, but the lower class, that lower category, it's a much larger bar, just width-wise, which is meaningless. There's nothing about the width that is informative about the data, and it implies many more observations in that lower category than actually exist. So this is really a violation of the area principle, because the size of the bar is not in relation to the magnitude of the value it represents. So in general, things to know for this discussion about categorical data when you have a single categorical data variable and you want to create a table or visualize it. A frequency table will give you the counts for each category of a categorical variable. To put it another way, a frequency table gives the counts for each level of a factor. It means the same thing. A relative frequency table will give you the proportions or percentages for each category or level of a categorical variable. And bar charts and pie graphs can be used to visualize a categorical variable, and in general, you should really strive to present information from your data set as clearly as possible without distortion. And with that, that concludes our discussion of part 1 in our broader discussion of categorical data.